Yeah. All right. Welcome back, everyone. Thanks for joining us here at another Silo seminar. This week, we're delighted to welcome Arash Amini. Arash is an associate professor of statistics at UCLA. Before that, he was a postdoc at the University of Michigan, and before that, he did his PhD at Berkeley. Today, he'll talk about graph neural networks and the effect of graph noise. Let's welcome Arash.
Thank you guys for inviting me. It's good to be here. I'm going to talk about today, hopefully, GNNs. And if you don't know about them, I'm hoping that you would learn a little bit about what GNNs are. And it's mostly about the result that we have on trying to understand the role of the depth or deep a GNN should be, and what basically the effect of the network or graph noise is. Hopefully that becomes clear as well. So this is joint work with Luciano Vinas, who's a PhD student graduating from our department hopefully this year. And he has done a lot of the technical aspects of the work. So the question basically, as I mentioned, is roughly is deeper better for graph? So there's this dogma in deep learning. If you know about deep learning, these neural networks that people start stacking. So you get layer by layer, and then what people observe is that deeper generally means better. In deep learning, there's this dogma: deeper is better, and so this hasn't been the case empirically for GNNs, graph neural networks. So people have observed these things called oversmoothing, which means that as you get deeper and deeper, the signal sort of kind of washes out, not unreasonably. And despite being sort of state of the art for graph learning, there's this issue that people have been grappling with. And so we wanted to understand maybe from a theoretical perspective, is there any like a small depth? Or another way, you pose it another way, is there a fundamental limit to the GNN performance? You can't just indefinitely increase the depth. And as a byproduct, you get the effect of graph noise, which we'll talk about. Okay, so that's the basic idea. So the problem that we kind of studied these on is this sort of simplified problem. Oftentimes they call it semi-supervised node classification here. So the inputs are listed there. So you have a graph, which is given in the form of an adjacency matrix. It's a binary, let's say, matrix n by n. And so the ijth entry tells you whether there's an edge between node I and j. Okay. So classical is sort of way of representing a graph as a matrix. And then you get node features. So X is a matrix. Let's say n by d. N is the number of nodes. E is the number of features. This is like a classical regression matrix, like the design matrix in regression. The rows are the features you get for each, basically, node. And then you get a label for each node by I. In the case of regression, it's a real value, let's say, parameter, like real value observation. In the case of classification, it's discrete. Let's say we focus on L-class classification. So that notation that I have there is like the set of 1 through L. Okay, so each node has this label. The thing is that you don't observe the labels for all the nodes, just a subset. So the labels are partially observed, the rest fully observed. And then the goal is to predict the remaining labels. Pretty kind of well-defined, simple sort of looking task. So far, so good.
Speak up a little bit.
Yes. Sorry.
Speak up a little bit.
Yes. Yeah. Right. I'll try. Yeah. So So let me tell you what a GNN is. So the way that the GNN would approach this is via a sort of message passing. So each node receives a message from its neighbors, and it aggregates the message, and based on that message, sort of predicts the label of the node. So imagine you have this node in the middle, and these vectors that you see here are the features of the nodes. And so if you focus on predicting the label of this node, the neighbors would send messages to this. What is the simplest message? The simplest message is just the feature of the node. So let's say they just send the features that they have to this node. Xj is the feature of the jth node. And then this guy does some sort of aggregation. The simplest aggregation is just to sum them, let's say. You can take the average, or you can do something else. But that would give you a new feature vector for this node. And so this is the simple procedure of message passing and aggregation. The sum over the neighbors of node I, all the features of neighbors. Or you can write it in the compact form. If you think about what the adjacency matrix does, you just multiply A on this side, whatever X that is. And then each row of this, so I star, this is like the ith row. So if you look at the ith row, it's just the same information. So it just sums basically rows of X, which are the features, over only the neighbors of node I. Okay, so that's the basic procedure of it, like a simplified GNN. Now, what can we do with this? We can just treat this as a new feature for node I and then run a regression or a classification on it. We get these aggregated features. If it was a regression, I just regress yi onto phi I. Okay, and then compactly, if you think about it, you can write it as basically yi is the ith row of a xw. W is a base vector. Okay, that's a simple G. Good so far.
It's a question about, I guess the features associated with each node and the adjacency matrix are somehow application dependent. Where's the adjacency come from? Do you have to? That's a given though.
That's part of your data, yes. So you're assuming that you observe this network, and you want to use this network information, right? So one way to solve this problem is to ignore the network information. Just let's say do a regression, classical regression. Yi is like xw I. So that's regression. That gives you a baseline. So the idea is that if you do this aggregation, potentially you do better because, let's say, you hope that the labels of nodes that are neighbors of this are similar, and then maybe the features are similar. Sounds good. So why this works? Here's a simple kind of model to see why this works. Consider a classification setting. So in the classification setting, this would be similar, but then you'd have a different loss. So this would be maybe the say binary classification. This would model the logits. So you have a loss between the yi's and the logits, the log nodes. So consider the L-class classification. Imagine that the xi's are generated by a mixture model. So they're compactly written in this format. So you have these centers of the clusters of mu1 up to mu L. And then node I, depending on its label, picks the center. So yi is the label of node I. So if I'm in class 2, let's say I pick mu2 and then plus some noise. That's the observation for them. Okay, that's the classical mixture model without a super random and y. They're writing it. So what happens if I do go through this averaging, message passing and averaging? So the feature of node I would be the sum of the xi's over the neighbors. And so you can just write it down. It would be this decomposition. It has this decomposition. So for a moment, imagine that the label of all my, like, look at node I, assume that the label of all the nodes that are connected to node I is the same as node I. Okay, so let's say we have two classes. Node I is in class 1. All the yj's, or j's in the neighbors of I are also 1. Okay, so then we're summing mu1 for all these guys, and so I get the cardinality of ni, which is the degree of node I times mu1. Okay, so that part is like degree of node I times mu1. This one, the sum of ei, iid, let's say, subcapital noise, and that part you see that like scales like root the number, how many numbers you have. So it scales like root di. So this gets amplified by di, this gets amplified by root di. So that's the classical idea in the statistics that if you sum or average noise, it gets better, things get better. So your signal relative to noise is scaled by a factor of root di. Okay, just do the simple analysis, and you see after one round of aggregation, you have a better signal to noise ratio if you have your degree is large. So the exact scale of the amplification is just root of the degree. So if you the average degree of the network, for example, grows, on average, everyone gets better, like better features, like less noisy features. So good. So far, so good. So the question is that if I repeat this process, what happens? But there was a caveat, so I assumed something here. If anyone saw the issue with this, yeah.
Mu's have to be sufficiently large.
Mu's don't have to be sufficient. Mu's could be fixed. So the aggregation produces like n, the cardinality of this set times mu.
So if you use like very close to 0, then it's going to be hard to.
So the thing is that the only thing that matters is that the difference between mu1 and mu2, let's say. And if it's close to 0, but it's like fixed, it's fine. Right. There's a fundamental issue with the argument that they made. Like there's an assumption that they made. Yes.
You said that the noise averages out. So what if all the noise is somewhat systematic and it's all in one direction? So then out to 0?
Yeah, so you can worry about that, but let's say we assume that the noise is independent. That's true. But then all your regressions would also be problematic. Everything in statistics would be problematic. You're assuming that like statisticians who make those assumptions were. So this is fine. There was another issue. What is
The outcomes to cluster on the network?
outcomes to cluster? The outcome here is just the label. Right?
Yeah, but if they aren't localized to specific parts of the network, then that should just be the same value across the whole, right?
Which one?
If the mu's in each neighborhood, they have to all be sort of like similar in each neighborhood.
No, mu's are like fixed. And so I'm assuming this particular model, right? I'm assuming this model. So everything here is given. Given this model, there was a tiny little assumption. I can reveal it, but just one guess.
The neighborhood sizes are diverging in N. We're using that to.
That's true. That's true. But that's a mild assumption that I'm gonna assume. There's a
Tell it to one of our reviewers.
Sorry. Yes. Yeah. The degree basically grows, or the neighborhood bigger. It could be getting very slowly bigger, like log n, even slower. For us, who has to be at least log n. So the thing to assume is that everyone in the neighborhood of node I is having the same label, which is not necessarily true. So if the network is not, maybe it's related to what you said, but if there are noisy connections, so I'm not necessarily connected only to my group, but to other groups as well, then when I aggregate, this is going to be a mix of mu1 and mu2. Okay, so I'm not going to get pure signal. And if I repeat this aggregation gets worse. And if you think about it, if you do it many times, you wash out. Basically, you get like a basically average, or if you divide by something, you get the average of all the groups. So then the network noise is what I'm talking about here. So the fact that not everyone that's in the neighborhood of node I is in the same cluster. So this also introduces that the first term has a noise in, which is due to noisy connections. And so that's what we refer to as graph noise. And as you repeat this process, that graph noise gets amplified. And it's not obvious, is there a right balance? So if I do it once, there's a bit of noise in there. Maybe at that point, I'm still good enough. But then if I repeat it, what would happen? How the noise amplified. So that's what we wanted to. Is this sort of setting clear? So that is the idea. So this is like a simple schematic of what happens. This is the same setting that I generated. I'm not showing the network here, but the network is the stochastic block model. Later we'll talk about that. 3 classes, original labels from mixture model, pretty mixed. And if you do one level of aggregation, just sort of separate out, which is what you roughly expect from that argument that I mentioned. And in this case, if you do it twice, they sort of seem to be slightly more spread out, but not too much. So from the visualization, it's hard to tell necessarily it's getting better or worse. But you wanted to understand the theoretical, like this picture more theoretical. Okay, so these experiments you can run for yourself. It's sort of kind of easy to visualize. So the next piece is like some empirical.
Just so you're saying if I kept going, eventually I just see a blob.
Eventually you should see a blob, sort of. Yes, that's the idea. Depends on the strength of the.
These are the features.
These are the aggregated features.
These are the 3-dimensional.
Yeah. These are these phi i's. And yeah.
I see. And they should just converge to one number, I guess.
Yes,
So they
yes.
should collapse to a point eventually. That you just reach a consensus. Or,
Right. But that it needs to run for a long.
yeah, for a long time, but they sort of
They should.
and then collapse.
Right. Yes. At least relative. So you can see also this is like scaling. Like the scale is becoming big. So a better way of doing it is to take the average, normalized by the degree, which would be equivalent to applying instead of a here, you would apply the random walk Laplace -1. And then you're doing a little bit of eigenvector analysis. So you converge to the rank 1 matrix, which is 1-1 transpose, which is just aggregate, like averaging, like 1-1 transpose over n. So you should see that.
So is that normalizing done or not?
Here it's not done, but it's the same idea. I mean,
But in graph room.
all of it is like. No, in reality, people plug in different things here, and then they choose the best based on the validations. Everything is fine. I believe.
Okay, sure.
Any other questions? Okay, so the next piece of sort of thing that caused like at least us to try to understand this is some empirical results that we had, which is I'm not going to go into details, but the columns here are some of the classical or sort of popular data sets that people use in science. They have these benchmarks. That's what the deep learning people do. They have these well-known benchmarks, and everyone tries their methods on them, and you get a state of the art basically at any point. Certain sort of methods sort of win, and at the time these were kind of state of the art, close to the state of the art. So Quora, CiteSeer, PubMed, these are citation networks. So paper cites what so nodes are papers, I believe. Connections are citations. Chameleon and Squirrel have Wikipedia pages, I think. Connections between Wikipedia pages on these topics, Squirrel and Chameleon. And so linear is just XW, that's linear regression. Aggregated linear is just AXW. That's like the basic linear GNN. Kernel and LR, low rank kernel, are methods that we propose separate paper, which add a little bit of nonlinearity, like spectral reshaping to A. But the main point, if you look at it, for example, with Chameleon, you see that there is a gap between linear and aggregated linear. So aggregated linear does a lot better. But it's actually doing much better than the state of the art as well. So these GNNs are very sophisticated GNNs. And if you look at some other ones, you can see the gap is not that, sometimes it's significant, sometimes it's not. So for example, here, it's like 82 versus 89. With the kernel approach, you reshape it a little bit, you get very close. So this one layer aggregation basically does a lot of work. So that was the idea, basically mainly these two works. You can see like aggregated linear sort of improves, and then these guys don't improve. The fact is that you could get roughly 78 from these if you do a better job at optimization. So Gianna have managed to figure out if you do early stuff, and these methods can achieve this as well. But the thing is that they achieve this with a lot more parameters and a lot more complexity. And so this observation, which a simple like aggregation, seems to perform almost at the level of GNNs, at least in some cases, cause us to try to understand, yes.
What are you aggregating here? Like, what's the covariate that's getting passed around the network?
That's a good question. I think these are binary features, very high dimensional, and they most likely encode sort of words. So it's like a bag of word models. They are actually similar in the nature. It's like it's a giant binary image. That's what I believe. Any other questions? Okay, so this is the empirical piece. And so, okay, so here are examples of simulations that we did on this so-called contextual stochastic block model, which I'm going to talk about. And you can see that as n increases here, when n increases, the degrees are also increasing a little bit. It's a tree class, and so tree classes, tree class classification. If you only use X, if you can use it as like a mixture model, if you train a mixture model, try to predict the labels, you can see that performance is around 64, 65, and it's stable because n doesn't have anything to do. There's no like information added as you increase n in trying to estimate the label of a single node. But these neural networks, so this is the state of the art, and the kernel one is just reshaping that aggregated linear that we proposed. And you can see that this is almost close to the state of the art, and the gap closes as in the method, like very close. This one, for example, still does a little bit better at moderate n. But as n grows and the degree grows, things basically start to look similar. And then this kernel method is basically using the same, at most, basically the total number of parameters is n. So like a non-parametric regression on this plus 12. But this one is using like an order of magnitude, 2 order of magnitude higher number of parameters. So, the complexity is not buying you that much performance. But this is, again, a simulated setting. So these, I should say, work necessarily, like they work better in practice, slightly better. But another evidence that maybe simpler. One layer aggregation is not that bad. Questions so far. So let's try to understand this from a empirical perspective. I need to introduce this multi-layer idea. So the multi-layer idea in our case would be very simple. We just do aggregation k times. You do the message passing k times, which is equivalent to applying a to the k to x, and then apply the weight. Okay. If you look at the GNN literature, what people actually do or started to do first is you apply a to x, you do aggregation, you apply weight on the side, and then you do some nonlinearity, and then do again a on this side, w on this side, nonlinearity side, w on this side. So there are some nonlinearities in between that prevents you from collapsing everything back. But if there is no nonlinearity, just everything collapses back into this simple formula. So you aggregate k times the features, and then run a regression or linear classification. So you might think this is simplistic, but this is actually used in practice. Like linear combination of these. These are called polynomial, what we call polynomial GNNs, but people, if you look at the spectral GNN literature, there are a lot of instances of this. They figured out that nonlinearity is not adding much, so they peeled it away. Some people call it linear GNN. It's clearly like polynomial in the kind of network parameter, like the network variable, the polynomial. So they're actually used in practice. So we want to understand what is the role of K. So if I keep doing this, do I get better? Okay, that's equivalent to the depth in. So the model is this contextual stochastic block model that I alluded to earlier. So if you look at the features are generated exactly as I introduced earlier. They're a mixture with centers mu1 to L, given the yi, which are the labels. I just have to tell you how the edges are created, and these are created from this well-known stochastic block model, which is just saying that the probability of a connection between I and J only depends on the labels. And so if I know the label of node I, yi, the label of node J, I'm going to go look into a matrix, which is like a E matrix, and choose that entry as the connection problem. Everything in like class 1 and class 2, for example, connects with the same probability to each other. So the level of the complexity is only this B. So that's the contextual, the generalized contextual block model. The original one, I think, is a paper in which you do the PQ SBM. So you just have P on the diagonal of that, and maybe just 2 classes. So the key parameters would be this sparsity parameter. So P max here is the maximum connection probability, and N times P is roughly a measure of degree, the maximum degree if you want, or something like that. It's not the maximum degree, but it measures the degree. So this new N, if it's of the order of n, the network is dense. If it's of the order of 1, it's very sparse. If it's something in between, closer to 1, let's say if it's log n, it's pretty sparse, but it's still growing. So that's the regime that we're going to look at. Sparse networks, but not too sparse that degree is common. L is the number of clusters. The feature noise we're going to assume to be sub-Gaussian, and we assume to be independent, like across the nodes. Okay. So what are we going to actually study? We're not going to study the kind of optimization aspects of it, which is basically just a linear. You can think of it as logistic regression or multinomial softmax regression in the L class classification. We're just going to look at the features. It would simplify the analysis. And what I want to look at is the signal to noise ratio, which is basically how far the centers are of these new clusters compared to the variance of each cluster. So, so if you look at this, phi ik, that's the itro of ak to the x. This is the k level aggregated feature. And if you look at the expectation of this, the expectation is with respect to the randomness of, let's say, A and the noise in the features. By symmetry of the block model, you can argue that these are going to be the same for every I in the same cluster. So every I in the same cluster would get the same expected phi ik, which we can treat as the center of that cluster. And we're going to denote as mu, let's say, k, if I is in the cluster. Okay, so this difference of 2 of these mu, the centers, if I and j are in different clusters. So that's the signal, basically, part. And then this is a measure of how far each of them is from the center. And this is some sort of an average distance of each feature to the center. So this quantity is a measure of signal to noise ratio as you take the minimum over all possible labels. So it's like all possible. So the denominator is fixed, the minimum fixed, this numerator is just all the pairwise new centers you look at divided by the variation. And then the rho here is noise to signal ratio. So we want the noise to signal ratio, the rho to go to 0, or the SNR to go to n. And if this quantity, for example, you can control this, if it goes to 0, you can show, for example, that the k-means succeeds. It's just k-means without ignoring the partial knowledge of the labels. So you don't even need the labels yi's, you can just do k. But in any case, this is the quantity that we look at, okay? How this is affected by k. Sounds good. Okay, so the statement result is simple, and it ended up, at least for us, was surprising, and then it's given in these two inequalities. So rho k, which is noise to signal ratio, if you multiply by root nu n was that sparsity measure. This is upper bounded and lower bounded by something which doesn't depend on n. There are these constants, it's a big constant which appears like in this like a symmetric fashion, this and the inverse of it. And these constants are sort of even less interesting, so they're closer. They're not numerical, but they're constants. So the only dependence in k is going to be in this constant. And this is going to be the rate that controls the SNR. So what this is saying is that the noise to signal ratio drops like 1 over root nu n, independent of k. Okay, so k has no effect on the rate that this SNR goes to 0. So there is fundamental SNR rate, which is not dependent on depth. And in particular, this root nu n is, if you follow the intuitive argument that I mentioned, it's easy to see when k is 1. One layer aggregation gives you this factor of root n, signal to noise ratio. The point of this result is that this is not going to change as you increase k. So adding more layers is not fundamentally going to change the rate. It's going to affect the constants potentially, so this depends on k, but the rate of convergence is not controlled by k. So first order aggregation is good, and as far as the rate goes, sort of is sufficient, it suggests. The other thing that this suggests is that the over smoothing that you see, that the signal just gets washed out, it's kind of it's like over smoothing is like it appears here, so in the C, and what it means is that it's going to go away. So this idea of being washed out goes away as the network grows. So if you fix k, and so if you fix n and keep doing it, the signal gets washed out. But if you fix k and let the network grow, your over smoothing effect goes away. You behave the same as a one layer aggregation. So there's no over smoothing issue. There's no issue, but there's no gain as well. So that's kind of the message. This is sort of hopefully clear. Okay, so it's clear. I can do different things. I can try to maybe give you some intuition of why this happens. So maybe I think I probably have 25. Okay. So I'm going to try to what I want to try to do is hopefully give you an idea of why this happens, or at least like a bit of the a little bit more detail about how we prove this, because I think the techniques are up to it. So there are some technical assumptions. So one of the assumptions is roughly that. So the first you can assume that all the b's grow like. So remember this nu n is like n times the maximum entry of b. This is assuming that you can assume that all the entries basically grow like nu n over n. But you can relax it a lot. You can relax it. Assume that for every L there is at least one B that grows like nu n. The rest are maybe of lower order. But for the like first sort of, if you want to just ignore that part, just assume that all the entries are like nu n over n up to some cost. Here to understand. There's some assumptions about Pi here is pi is the proportion of the L class. How many nodes are in L class? This has to be lower bounded, sort of upper bounded. There is this because constraints are new. The second one is the more important one. These are sort of some sort of a. I have the definition. I don't have the definition of these here, but these are basically roughly what happens when you pass these mu's through the K aggregated version of B. So it's a lower dimensional version of the aggregation. Instead of at the level of N, it occurs at the level of community. And so you need some sort of separation. So it could be that the connections sort of don't mesh well. So the B matrix doesn't mesh well with mu, so you'd lose information. I could do one layer aggregation and lose all the information. So there's some sort of a catastrophic sort of reduction that could happen. This prevents that. So it says that if you pass the mu's through B K times, they're still separated enough. Okay, it's kind of unavoidable. So the way that we use these, like the way that we can prove this is first you prove a signal bound, which is look at the differences of these centers. So these are the expected values of phi's. And if you look at the difference of the centers for L and L prime, what you can show is that this difference grows like nu n over to the k. So that's the scale of the signal, nu n to the k. And I might say a few words, and you can see the constants that appear here depend on k. So that quantity ck also implicit. CQC is this lower one, which also independently, like implicitly depends on k. But you can see that the dependence on n is like nu n over nu n to the k. I might say a few words about how you can prove this. It's not that difficult. The more difficult one is controlling the noise. So what we can show is the noise with high probability is bounded above and below like this. So roughly speaking, the noise grows like nu n to the k minus 1/2. So the signal goes like nu n to the k, noise grows like nu n to the k minus 1/2. So if you divide the signal to noise, like to form the signal to noise ratio, this nu n to the k goes away. So what you end up having is something like this. So D is the noise. So this divided by that, so you get 1 over root. Okay. And I want to maybe talk a little bit about there are some technical conditions. So nu n, you can see at least has to grow like log n. N has to grow, at least has to be lower bounded. There's some order moment condition, which is this is generally true if nu n goes to infinity. Okay, so I want to talk a little bit about how this particular result will be done, and maybe at the end. So the main idea comes from like matrix, random matrix theory, which is because we're looking at the polynomials of A, you can write them. Okay, so here's a very simple like explanation. If you look at A to the K, if you look at the ij element, just expand this. You can write it as I had a board. Can you write on the board? If you look at, for example, A squared, right? If you look at ij, this would be AI, let's say, we call this I2, and then A I2J, okay. I2 from 1 to 9. Right, classical, just definition. So you can think of it as basically looking at all the walks of length 2 from I to J. And the only thing that matters here is this middle node. If I look at A to the 3, right, I get sigma A I1 AI1, I2, and then AI2J, or I1 and I2. So I'll be looking at walks of length. This is length 2, this is length 3. Okay, so you're looking at walks of length 3 that go from I to J. And for example, if I want to control the expected value of this is not exactly the quantity, but this also comes up. When you try to control the noise feature, you have to control this. I get expectation here. And because these are binary variables, this is just the probability, because they're all 0 and 1. This is equivalent to like the probability that all these edges happen. So AI1 and I2 and AI2J all are 1. This is the same as the probability that basically observe this particular walk in the graph. So it's a random graph that you observe. And the expectation of this is the probability to observe. So I give you a particular, for example, graph. And maybe this walk is, so this is I, this is J. Maybe this walk is, maybe looking at this. This walk is this one. So this one doesn't happen in this particular graph. But there's a chance that this happens based on the random model. And this is just measuring them. So the idea is that you will look at these walks and you have to count how many there are and the probability of them. And these would kind of give you a trade-off. So because each so this is, let's say if you look at a walk, it could go like it could go on an edge and come back and go back to your position. So there's no need for these walks to be the edges to be unique. Okay, so if I look at the k a to the k, it's going to be a k walk. So it's going to be k walk, and some of these edges would be repeated. So the number of unique edges. So if they're repeated, you get, for example, this to the 2, this to the 3, this to the 4. Just because they're binary, it just doesn't matter. So it would be like the probability would depend on the number of unique edges. And because each one of these have probability like nu n over n, if the number of unique edges is t, the probability of this walk appearing would be nu n to the n. So the more unique edges you have, the lower the probability. This is like something less than 1. So the more unique edges you have, the less likely that that particular walk appears. So you're gonna look at different walks. Walks is like with unique number of edges t, and for all the walks that have t unique edges, that's the probability of them appearing, and then you have to count how many they are, and then you can control, for example, this expectation. Okay, if you have a lot of unique edges, this would be small, but there's a lot of configurations because there's going to be a lot of nodes here, and then you roughly have like n to whatever combinations that you can put there. So you get a lot of configurations but with lower probability. If t is low, you get higher probability but lower configuration. So the count and then the number of unique edges would sort of trade off. And then based on these considerations, we can figure out what is the maximal, what kind of, so these walks would produce, but these walks would produce graphs. So depending on, so if you look at this walk, there's some repeated edges. If I just look at the graph that it induces, ignore the direction and ignore the repeated edges, it induces a graph. So this captures the kind of the probabilistic aspect. So how many unique edges it has is 4, and so it's in this would be like p to the 4 is the probability, like nu n over n to the 4. So you want graphs like if I have k edges, you want graphs that have like kind of maximal number of nodes but least amount of edges. Okay, so there's like a node to vertex ratio optimality, which if you think about it, trees or paths, these are the optimal structures. So something like this is not optimal. Something like this, like a path would be more like dominant in terms of contribution. So cycles you can get rid of. So you can ignore all the things that are not, like for example, trees or paths, and then just the dominant structures would be certain paths or certain trees. So that's basically the rough idea. So you look at these blocks, and if you want to have to characterize the dominant term, you want the blocks to have many configurations, because then the summation gives you a lot, like the count. So it's like count times the probability. So many configurations, this increases the count. And for that, you need a lot of sort of vertices. You want to maximize the number of vertices. To increase this, you want minimal number of edges. Minimize the number of unique edges. And so this leads to characterization of what graph structure would give you the dominant term. And then once you realize that, then you can just ignore everything else, just focus on that. Okay, so that's the rough idea. Okay, let me go back. So is this sort of clear? That's the rough idea. So for example, if you do, let me give you a little more detail. So if you look at the noise deviation, what you can do is you can decompose it into this format. Add and subtract. It's a little bit more tricky, but this is an exact decomposition. If you look at this, this is controlling or looking at the deviation of AK and the expectation of A to the K. And so this we call the graph noise, because here the deviation of A to the K from the ideal expectation is controlling this term. And this would be pure like feature noise. So this one you can analyze using the ideas that I mentioned. This is the sum of, let's say, independent sub-Gaussian variables, and it would have the sub-Gaussian parameter, which would be this to the power, basically this squared, summation of these squared would be like the variance of this. So if you control these quantities that I mentioned, which you can do by that argument that I did, you can control this term. So expectation of A to the K. Ij is controlled by counting how many walks, dominant walks there are, and the probabilities is roughly clear. So you can control this term using that argument. To control this term, it would be a little more tricky because why would it be more tricky? But any questions? So this argument, little argument that I did, we would take care of this. But you still have to count. So this is the rough idea. So nu n to the n to the t is the number of walks with p unique edges. You get this, but you have to count how many walks from I to j unique edges. And there's some interesting combinatorial problems that have appear here. So whether there's loops in the walks or not, there are some sort of interesting sort of cases where the case where I goes back to, so I and j are the same. The diagonal elements are tricky. But I'm not going to go into this because I can try to remember. But this takes care of that feature noise. Needed. So the more interesting part is the graph noise, in which in order to control this, what we do is, what do? We do, this is a random quantity. I want to control, I want to like a concentration result for this. What I can do is I can look at the moment. I raise this to the power of r. So instead of, so here it was easy because I could take the expectation. It's like expectation is there, I just have to control. So, write it down. This guy is sub-Gaussian with parameter which is expectation of A to the K ij squared root or like, yeah, something like So once you control this, you have a concentration from sub-Gaussian concentration. This one is more difficult. This is not sub-Gaussian because this decay sort of gets heavier tail. So what we do is, if you call that particular part delta, as we call this delta IM, this is a random quantity. We raise it to the power r, r being odd, sorry, r even, and study the rth moment. So if you control the rth moment, then you can get concentration from moments. So if you can control the moments, for example, if you know the moments grow like, I think r to the r over 2, then this would be sub-Gaussian. If it's like heavier tail, it would be going fast. So, but controlling this would allow you to get a concentration equality. So what happens is once you raise this to the power r, you can see these are a to the k already, and then there's a sum over like raised to the power r, you get basically instead of a single walk, you get r walks of length k. So you end up with, once you expand, you end up with this nice quantity. You get a summation over all walk sequences of length r, where each element in this sequence is a k walk. Okay, so before we had just a single k walk, now we have r k walks, and then they can share edges between and across. And then you play the same game. And then this last one is just at the end of the walk basically is free. So you start from, before it was start from I and then j. Here you start from I, the last piece could pick any of the x's. So this is projection onto the last element of the last walk, or each walk basically. So there's this complication as well, but that's not crucial. The thing is that you have to study the combinatorics of these walk sequences. And you can play the same game. So here's like a set of 6 walk sequences of length 3 each. So here I'm considering the 6th moment of a certain, like this guy, for example, r is 6. I have to look at 6 r sequences, and k here would be 3, because I'm looking at walks of length 3. And overall, these walk sequences induce a graph. Okay, this is I'm considering all the edges, like for example 1 and 2, 2 and 3, and 3 and 5. That's the first walk, and so on. You can see there are some repetitions. I ignore the repetitions. So this is like 1 and 2, and then 4 and 6. So once you write down everything, and then you get a graph. Okay, and the structure of this graph determines the which walk sequences in that sum are dominant. So you can argue similarly based on the probabilities. You have to count how many unique edges there are, but I think you would also consider, so how many unique edges? This is the number of unique edges among all this walk sequence, and how many vertices that they have. And then you can argue that if the walk sequences are not overlapping because of the centering, the contribution would be 0. So you need at least some overlap. At least, I believe, any pair of walks, I think, has to overlap in one edge. If one of the walks does not overlap with any one of the other ones, you can just throw it out. So we focus on overlapping walks. And so it end up, they induce a partition. So based on so all the walks that overlap would create a partition or the equivalence class basically. So you can see these 2 walks overlap at this, so they're in one element of the partition, and these 2 are in another element and in another element. So the walk sequences that overlap partition the sequence 1 up to r. Into like a partition, give you a partition. And it turns out that the dominant walks correspond to the case where the partition exactly has 2 elements in each piece. So it's a perfect matching basically. So you can argue that the dominant walks would be the case where only it wouldn't be the case that the 3 walks share an edge. That's not dominant. At most, or exactly 2 of them have to share an edge of 2 and 2. Okay, so a perfect matching of on this would be a dominant walk, and the structure really looks like this. So the thing that I draw in this case is the structure of the graph for the dominant block. There's only one. If you ignore the labels, there's only one structure. And what it does is you have to have it. The first edge has to be overlapping, and then there's no overlap. So you end up having like a perfect matching, a perfect partition of these block sequence of two pairs, and a pair would share the first outgoing edge from I, and then no other sharing. So this can't come back. So you have these angle like from. So there's a corresponding, and there's these branches. And once you figure out that this is the only case, then you count how many configurations there are. So I can have the configurations are, because I have n nodes, I can like put different labels on this, and all the configurations you can count. And basically you get a perfect, sort of almost perfect characterization of the dominant term, and then the rest are like lower order. So this would contribute nu n to the rk minus r over 2. That's the probability of the vector happening. You can see it's like probably like to the r, and then the rest of it is only dependent on r. And so from that you get a concentration of with this being like play the role of the variance. Sounds good. So that's the basic idea. So basically combinatorics of walks and considering the probability and configurations basically leads to the idea of trying to partition the walks based on the number of unique edges and the number of vertices, and then figure out what is the right structure. And the overlapping part sort of is like a bonus because of the zero meanness. You don't have to worry about the walks that don't overlap, and so on. Okay. This is how you can get from some sort of a result like concentration of the. If you have a certain kind of this pattern of moment growth, you get a concentration which is kind of potentially this could be something other than 2. If it's 2, it's sub-Gaussian, but if it's higher than 2, sometimes they call it sub-Babel concentration. It turns out in the regime it's going to be sub-Gaussian for us, but I don't have time. I'm going to skip the signal part. Okay, so maybe in the last 2 minutes, where can we go from here? So interestingly, if you look at again the characterization of the dominant block, it gives you more information than what we just proved. It not only gives you this, but because these are perfect matching. If you remember, anyone remembers the number of how many perfect matching of this set there are? Anyone knows? The combinatorial question. If you have a set of, so perfect matching would be 1, 2, 3, 4, 5. It has to be. Okay, so one perfect matching is like 1, 3, 2, 4, 5, 6. Right? So you have to pair them such that everyone is paired, and then nothing is left out. So how many perfect matchings on this? I didn't know this, but so if this is R, the number of perfect matchings is R minus 1 double factorial. It's just all the products of all the odds, odd numbers. So it would be like 1 times 3 times 5, 15 perfect matchings. Yeah. And this turns out to be the moments of a certain random variable. If anyone remembers, like what random variable has the even moments that are like this. So a Gaussian would have, so if I have a Gaussian, this is a way that you can prove CFP. So that if R is even, this would be R minus 1. Double factorial. If R is 0, sorry, if R is odd, this would be 0. Okay, so what ended up happening is that because, I mean, this is the structure, you count them, you get R minus 1 factorial. And then you do some sort of take care of the rest of the ideas, and then you get kind of a CLP. Because the moments grow like this, but there's also some other action going on here. So if I normalize these features by this scale factor. And if we try to look at the empirical distribution, the empirical distribution converges something which is a mixture of Gaussian, but it's not the usual mixture, it's just a scale mixture. So it makes it somehow non-trivial. So it's zero mean, but the variances are different. And you can see this if you play with the parameters, you'd see this scale mixture here. So that's the consequence of these results. And so this is ongoing work. So not all the details are fleshed out, but that's one way that you can go with this. So I'm going to stop. So what we show is like those rate invariance. And the idea is using these block combinatorics of all. And as a result, you get like a very complete characterization of dominant noise term, which, among other things, could produce non-trivial CLTs for these polynomial GNNs. And there's some potential interesting extensions. Can it be extended to non-polynomial GNNs? I don't know. Can we fix this gap issue? Can you design this so that the gap in the signal grows faster than the noise? This would be very interesting. Again, I don't know. But there seems to be also much more interesting general CLTs at play. For these, we have some ideas, but still like very crude. That's basically it. Practical aspects. So there's some of the literatures. There's some past work on this. And the main result was from this. Hopefully there's this paper coming soon about the CLT version. Thank you for your attention and have a nice day.
In the interest of time, if you have questions, please feel free to hang around. Otherwise, thanks a lot for joining us.